So that means in some complexes, we can take only one metal atom. Those are called as mononuclear carbonate compounds. In some compounds, we can take two or more than two nucleus. Those are called as dinuclear carbonate compounds as well as tetranuclear carbonate compounds. So look at this picture. In this picture, these are the examples for mononuclear carbonyl compounds because only one nuclear is present. Then the bottom one is example for dinuclear dinuclear carbonyl compounds. Then this is regarding for the trinuclear carbonyl compound. Okay. Then in this topic we are discussing yesterday, that is 18 valency electron rule. What is 18 valency electron rule? The number of electrons present in the outermost shell of the metal atom plus the ligand donated electrons. These two are equals to the 18, then it is called as a stable complex. Okay, so in this we are discussing these type of examples. Then we are discussing the preparation of and the properties of the nickel tetracarbonate. So three preparation methods as well as the properties we are discussing in the yesterday class. Then today we are discussing about the bonding modes of metal nitrosyls. Okay, how the metal nitrosyl is reacted with metal and produce the complex, as well as we are discussing about the MOED diagram of the nitrosyl compound. Look at this. The nitric acid, like carbon monoxide, forms complexes with the metal in their low oxidation state. The complexes of nitric oxide with metals are called as metal nitrosyls. Okay, the nitric oxide is reacted with a metal and produce a complex that is called as metal nitrosyl. So this is the metal atom. This is the nitrosyl. The nitrosyl donate the electrons to metal and produce a coordinate covalent bond. This type of complexes are called as metal nitrosyls. Okay, so here nitric oxide contains one more electron than the carbon monoxide, and as can be seen from the molecular orbital energy level diagram, this electron is present in pi star orbital. Thus, NO nitric oxide is 3 electron donor. Okay, the nitric oxide is 3 electron donor. The nitrogen ligands are well characterized, but many mixed nitrosyl complexes are known. Those are the iron pentacarbonate. It is reacted with nitrosyl ligand, then it is converted to dicarbonate, dinitrosyl, iron complex. The complex also produced the complex. Okay, although the nitrosyl group generally occurs as terminal ligands, bridging nitrosyl are also known. So this is about the structure belongs to the terminal nitrosyl, bridging nitrosyl is present. Look at this. In this, the two chromium metals are bonded with the two nitrosyl groups by using a bridge. This type of ligands are called as bridging ligands. How we can know which one is the bridge and which one is the terminal? Based upon the frequency values or IR stretching values, we can know the which one is the terminal and which one is the binding, bridging group. Okay. The next one is that, look at this. Since the nitrosyl cation, that is NO plus, NO is called as nitrosyl. If NO is having any positive charge, it is called as nitrosyl cation. Is a isoelectric with carbon monoxide. It is not surprising that there is a great similarity in the behavior of the two ligands. They each have 3 bonding pairs between the atoms and lone pairs on the both atoms. Although either atoms in nitrosyl is potential donor. The nitrosyl ligand bonding to metal, 2 types of modes of bondings are present, that is linear nitrosyl and bent nitrosyl groups. Okay, the nitrosyl ligand, when it is bonded by the 2 types of mode, one is linear nitrosyl, another one is bent nitrosyl group. The linear nitrogen group ligand is involved in the sp hybridization and it shows the 3 electron donor character. Look at this structure. In this structure, the metal atom is reacted with nitrosyl, that is N triple bond O. Wait. So here in this structure, the nitrosyl donate the nitrogen pair of electrons to metal atom and produce a bond in between the metal and nitrogen. Okay. At that moment, the nitrogen donates itself pair of electrons. Then the density of the nitrogen atom is decreases and the bonds are increases. So due to that reason, it gets instability and it carries the positive charge. That's why this metal atom again donate 1 pair of electron in between the nitrogen and the metal, then a double bond is takes place. Okay, so this type of resonance is observed in the metal and the nitrosyl. Okay. Then next, these are some of the examples for bent sp2 hybridization is like this. And this is about the straight bond in between the metal and nitrosyl ligand. The nitrosyl cation is isoelectronic with carbon monoxide bonding can be considered as a similar fashion to electron sigma donor with a strong pi acceptor ability. The straight mode of bonding, the nitrosyl is considered as nitrosyl cation, it is 3 electron donor. Okay. So in case of bent arrangement, NO behave as NO plus. Thus, it acts as a single electron donor. Because NO plus plus is indication of the deficiency. Okay, it is having the less number of electrons. So that's why it donates only a single electron but not the pair of electrons when it is bonded to the metal complexes. So the NO plus is a good sigma donor and pi good acceptor. Okay, so that's why the NO ligand bonded to metal complexes generally occur as terminal ligand and bridging ligand are also. Okay, so due to this reason, it is acting as the acceptor as well as the donor. Sigma donor, pi acceptor. So due to the dual nature, it reacted with the terminal ligand as well as the bridging ligand. Next topic is about this is about the MOED diagram of nitrosine. Already we know that in this the clear structure is given. The nitrogen atomic number. So this one is the atomic number. Okay, nitrogen atomic number, it is 7. Its electronic configuration 1s2, 2s2 and 2p3. Then oxygen, the right side oxygen atom is present. Its atomic number is 8 and electronic configuration is 1s2, 2s2, 2p4. Okay, so first you take like this in your examination. So this is about here you write 2 electrons. Make it like this and you write 2 electrons. Here also you write 2 electrons. Then 2s also having 2s also having 2 electrons. Then here you will write this one. So in this, the p orbital is having 3 electrons, but in this, the p orbital is having the 4 electrons. Okay. After that, you can write like this. So here it is having the 2 electrons, 1, 2, 1, 2. Here also 2 electrons, 1, 2, 1, 2. Then here totally 3 electrons, 1, 2, 3. Here 4 electrons, 1, 2, 3. Then 4th electron should be paired. So the p orbital, it is having the px orbital, py orbital as well as pz orbital. Okay. So in nitrogen atom, the px orbital is having 1 electron, py orbital is having 1 electron, pz orbital also having 1 electron. But for oxygen atom, the px orbital is having the 2 electrons, py is 1 electron, pz is 1 electron. Okay. So here then these electrons are distributed into the orbitals. So here this is in S1s orbital, it is having the 2 electrons, this is having the 2 electrons. So from these 4 electrons, the 1 electron from the 1s of the nitrogen and 1 electron from the 1s of the oxygen atom comes here. This is called as sigma 1s. Okay. Then next, in this 1s, another 2 electrons are there. So the next 1s electron from the nitrogen and 1s electron from the oxygen. These are like this. Then it is called as sigma star 1s. Okay. Sigma 1s is having the 2 electrons. Sigma star 1s also having 2 electrons. Sigma 1s is called as lower and a non-bonding orbital, and the sigma star 1s is called as non-bonding orbital. Then let's take 2s. 2s also like this. Here the confusion writing is they are writing. Actually, this is like this. In 2s orbital also, oxygen atom is, nitrogen atom is having the 2 electron and oxygen also having 2 electrons. Okay. In these two, in total number of electrons are 4. So 1 electron of the nitrogen, 1 electron of the oxygen is entering into the bonding orbital. This is called as sigma 2s. Okay. Then the remaining one electron of the nitrogen and remaining one electron of the oxygen enter into the anti-bonding orbital, that is called as sigma star 2s. Okay. Then this is up to the 1s, 2s. Then move to 2p orbital. Okay. Naira pitch. Then take this in the nitrogen atom, the p orbital is having the 3 electrons and the d orbital is having the 4 electrons. So in these orbitals, what happens? The p orbital from the px, actually it is classified like this. Okay, in this, these are called as, these two are called as bonding molecular orbital. Those are pi to px, pi to py. The above one is pi to pz. Okay. Then here it is pi star to px, pi star to py. Then this one is the pi star to pz. Okay. So let us see here in nitrogen atom, only 3 electrons are there. Okay, I write here the electrons 1, 2, 3. Okay, totally 3 electrons. In this oxygen atom, 4 electrons are there. 1, 2, 3, 4. Okay. So 1 electron of the nitrogen enter into the px to px orbital, pi to px, and 1 electron of the oxygen. So like this, totally 4 plus 3, 7 electrons are present. 1, 2, 3, 4, 5, 6. The 7th electron is enter into the pi star orbital. Okay. So this type of MOED diagram is produced. Okay, then after the electron should be filled, then we can calculate the bond order of the complex. So in this bond order, the bond order is equals to 1/2 into bonding molecular orbital minus anti-bonding molecular orbitals. Okay. Based upon the bonding molecular orbitals and anti-bonding molecular orbitals, we can calculate the bond order of the complex. So how we can calculate? That is, already we studied that. That is, the sigma 1s is having 2 electrons, sigma star 1s is having 2 electrons, sigma 2s is having 2 electrons, sigma star 2s is having 2 electrons, then pi to py, pi to px 2 electrons, pi to py 2 electrons, and pi to px 2 electrons, pi to py 2 electrons, then pi to pz, pi to pz, it is also having 2 electrons, as well as pi star to px, it is having 1 electron. Then the star mark containing electrons are called as non-burning electrons, and the normal one are called as burning orbitals electrons. Okay, here, so this is 1s2, then 2s2, 2px2, 2py2, as well as 2pz2. Totally 1, 2, 3, 4, 5 pairs. That is equals half into 10 minus in anti-bonding molecular orbital is represented by the star mark, that is this star 1s2, 2s2 and 2px1, totally 5. 10 minus 5. Look at this, I write here also, half into 10 minus 5, that is equals 5 by 2. Okay, this is okay, this is the calculation of the MOED diagrams bond order. Okay, the next, these are the sum of the complexes. This is square pyramidal shape. In this, the pent bond is present. Okay, this is regarding for the first chapter, that is metal carbonyls and nitrogens. So once I repeat, in this metal carbonyls and nitrogens, we are discussing about the MOED diagram of the both carbon monoxide as well as nitrogen liquid. Okay. Then next, how many types of bonds are produced by the carbonyl ligand as well as the nitrogen ligand. Then next, how many based upon the nucleus, that means it is the while it is the mononuclear, it is the dinuclear or trinuclear. So based upon that also we can give the classification of carbonyl compounds. Then next we are discussing about the in that carbonyl 18 valency electron rule. It is also called as 18 valency electron rule. In this 18 valency electron rule, the metal atoms outermost shell electrons plus ligand donated electrons both are equal to the 18, then it is called as a stable complex. Then we are discussing about the preparation and properties of the nickel tetracarbonate. Then in this nitrosyl also we are discussing about the terminal bonds as well as the bridging bond. Those are recorded by using the spectrum. Okay, so these topics we are discussed in this class. Then the next topic is about the non-aqueous solvent, and in this we are discussing about which are called as non-aqueous solvent and what are the uses of non-aqueous solvents. What is the classification of non-aqueous solvent? Okay. So here the first is about non-aqueous solvent. So non-aqueous solvents. Look at this. The most of the chemical reactions takes place in aqueous solution. Okay, most of the chemical reactions takes place in aqueous solution. Many chemical reactions require suitable solvent that is water. Water is considered as a universal solvent due to the most chemical substances dissolved in. Okay. Generally, the chemicals are dissolved in the suitable solvent. Water is acting as the universal solvent because the water, so many substances are dissolved in the water. So that's why it is called as universal solvent. Further, most common laboratory chemical reactions take place in water medium. Many chemical reactions also takes place in non-aqueous solvents like ammonia, sulfur dioxide, hydrogen chloride, etc. Okay. Generally, the most of the chemical reactions are also takes place in the non-aqueous solvent. The example of the non-aqueous solvents are ammonia, sulfur dioxide, hydrogen chloride. Okay. And what is the classification of solvents? So the solvents are classified into various types. Number one is based on the proton donating and as well as accepting property of solvent. First one is based on the proton donating and accepting property of the solvent. So based upon this property, these are classified into three types. One is protic solvent, another one is aprotic solvent, number three is amphoteric solvent. And which one is called as aprotic solvent or proton donating solvent? Protic solvent is called as proton donating solvent. These solvents containing hydrogen and able to release the proton are called protic solvents. Once I repeat, the solvents which are having the hydrogen atom and this hydrogen atom is eliminated as proton, that means H plus. Those are called as protic solvents. So these protic solvents are again classified into two types, acidic solvents and basic solvents. In acidic solvents, for example, we can take the sulfuric acid, acetic acid, okay, and hydrogen chloride. In this, they are having the strong tendency to donate the protons, okay, which are called as acidic solvents. The solvents which are having a strong tendency to donate the proton. Suppose we can take sulfuric acid. The formula is H2SO4. It is easily ready to donate the proton and it is converted to H plus and HSO4 minus. H plus is called as proton. So it is donate the proton and it is the acid. So that's why it is called as acidic proton. And a basic solvent. Basic solvent is nothing but it is having the base nature and it accepts the proton, then only it is converted to protic solvent. For example, we can take ammonia, NH3, then it is reacted with proton, then it is converted to NH4 plus. At that moment, it is acting as a protic solvent because it is plus charge is indication of protic nature. Okay. Then the second one is aprotic solvents. These are called as non-protic solvents. So it is reversed to the protic solvent. So the solvents which do not able to release the hydrogen atom are called as non-protic solvent. For example, carbon tetrachloride, benzene, chloroform, sulfur dioxide, nitrogen dioxide. All these doesn't release the proton. So that's why these are called as aprotic solvents. Okay. Then third one is amphoteric solvent. Amphoteric is nothing but based upon the reaction condition. It may be donate or it may be accept the proton. So that is called as amphoteric solvent. So this is one character. Then second phenomena is that based on the fact that like or dissolves like dissolves like. The solvents are classified into different types. Number one is ionizing solvents. So here in these ionizing solvents, these are compulsory, they are acting as the polar behavior or ionic nature. Hence only they are dissolved in the compounds. For example, we can take H2O plus H2O. Then it is converted to H3O plus OH minus. Okay. Any 2 moles of NH3 is dissolved, then it is converted to ammonium ions and amide ions. Okay, so based upon the ionizing capacity, we can explain the solvent. That is called as ionizing solvent. The non-ionizing solvent. For example, we can take the benzene, carbon tetrachloride. These are not involved in the ionization. So that's why these are called as non-ionizing solvents. The next third classification is that aqueous and non-aqueous solvent. So the solvents other than the water is called as non-aqueous solvent. Water solvent is called as aqueous solvent. Other than the water are called as non-aqueous solvents. Okay, once I repeat the classification, the solvents are mainly classified into 3 types. Number one is based upon the proton donating and proton accepting property. Number 2 is based upon the like dissolves like property. Number 3 is based upon the aqueous and non-aqueous solvent. So in that, the first one is based upon the proton donating and proton accepting. It is classified into 3 types: protic solvents, aprotic solvents, amphoteric solvents. Based upon the like, dislike, dissolves like, it is 2 types: ionizing solvents and non-ionizing solvents. And based upon the aqueous and non-aqueous nature, it is aqueous is called as water, non-aqueous is called as drinking water. Then the next topic is about the characteristics of solvent. So what are the characteristics of solvent? For example, some solvents like water, ammonia, hydrogen chloride, the physical properties are summarized in this table. Look at this table. In this table, the solvents are water, ammonia, and hydrogen chloride. The viscosity of water is 10.08, ammonia is 2.65, then HF is 2.40. Like this, we can know the dipole moment, dielectric constant, melting point, boiling point, as well as density. Look at this, the viscosity is very high. Then the density is also like vice versa. So in this, the water melting point is 273, ammonia 195, HF minus 89. Then the next reactions are autoionization. What is autoionization? What is dipole moment? What is dielectric constant? At the end, what is viscosity and what is conductivity? So these terminology words are discussed in this class. So here the first one is autoionization. The solvents like ammonia, hydrogen fluoride, and water are undergoes autoionization. One of the proton transfer between 2 molecules in liquid phase as indicated by the equilibrium. For example, we can take 2 moles of water. It is involved in the autoionization, then it is converted to H3O plus and hydroxyl ion. If we can take the 2 moles of ammonia, it is converted to ammonium cation as well as NH2 minus hydroxyl ion. Okay, amide ion, sorry. Then hydrogen fluoride, it is converted to H2F plus as well as F minus. Sulfur dioxide also like this. So these are themselves only dissolved. So that's why it is called as auto ionization. Then next is about the dipole moment. Solvents having higher values of dipole moment dissolve the polar substances readily. Okay, the solvents which are having the high dipole moment, they are easily dissolved in the polar substances. Okay, the dipole moment values of the solvent also gives an idea about the extent of association in the liquid state and hence its liquid temperature range. Okay. The next is about, okay, once I repeat, autoionization is nothing but the same atoms are involved in the ionization and they produce the product. When the dipole moment of the solvent is very high, then it is easily dissolved in the polar substance. Then next discussing about dielectric constant. So the dielectric constant, that is the Coulombic force of attraction between the cations and anions in an ionic crystal is given by the expression. So here F is equals Q plus Q minus. Q plus and Q minus are called as the cation and the anions. Then D R square. In this, the D is called as dielectric constant and R is called as the distance between the cation and anion. So based upon this, we can calculate the Coulombic attraction force. Okay. So in this, the F is directly proportional to IB because the F is inversely proportional to the dielectric constant of the solvent. Okay. So accordingly, a solvent with a large dielectric constant is expected to be a good solvent. Okay. Accordingly, a solvent with large dielectric constant, the solvent which is having the large dielectric constant is acting as a good solvent for an electrovalent compound and solution process is one in which attraction between ions is frequent. The solvents with small dielectric constant are poor solvent for ionic substances. For example, water which is greater value of dielectric constant than the liquid ammonia. So it is better solvent for dissolving ionic compounds like sodium chloride. Okay. Look at this. In this, the dielectric constant value is which one is having the more, that is easily acting as the best solvent. For example, water and ammonia, the water dielectric constant is 78.5 and ammonia is 20. So due to that reason, the water is acting as a good solvent and sodium chloride is easily dissolved in water, but the sodium chloride is not able to dissolve in ammonia due to the less dielectric constant. The next is about viscosity. The viscosity is an important property. The viscosity is an important property of a liquid solvent. Okay. Viscosity is also an important property of the liquid solvent. Some solvents are highly fluid in nature. For example, water, low molecular weight alcohols, liquid ammonia, while some are viscous. For example, anhydrous sulfuric acid, and higher molecular weight alcohols, etc. The solvents with low viscosity can be handled rather easily. On the other hand, precipitation, crystallization, and filtration are carried out with considerably difficult in solvent of high viscosity. Okay, look at this. Generally, viscosity is nothing but the substance which is having the viscous nature. Okay, so here the water molecule is having high fluid in nature. Okay, due to that reason, suppose we can take the sulfuric acid, which is having more viscous nature when comparing it to the water. Okay, some components are having the high viscous nature and some compounds are having the less viscosity character. The conductivity. These solvents are self-ionizing, hence electrical conductance give an idea about the extent of such ionization. Greater is ionization, easier it is for acid-base reactions to occur in the solvent. Okay, once I repeat, the solvents are self-ionizing, hence electrical conductance gives an idea about the extent of such ionization. Generally, the solvents are having the conductance nature. Due to the conductance nature only, they are behave as the acid or base and easily dissolve in the solvent. Then the next topic is about liquid ammonia. Liquid ammonia, it is taken as a solvent. Why we can use ammonia as a solvent? The first one is about physical properties. Liquid ammonia is a well-studied non-aqueous solvent. Okay, this liquid ammonia is a well-studied non-aqueous solvent. It is a protic solvent because it releases the proton. Many substances are soluble in liquid ammonia. Its freezing point is 173.5 Kelvin and boiling point is 239.62 Kelvin. And its dielectric constant is 23 and conductivity is 5 into 10 to the power of minus 11 ohm universe centimeter universe. Okay. The liquid ammonia, because of low dielectric constant, is a poor solvent for inorganic substances, which are generally ionic in nature. The order of solubility of halide is iodides are having more dissolved in iodides than comparing with bromides, chlorides, and fluorides. As covalent character of substances increases, their solubility in liquid ammonia is increases. Okay. The hydroxides, sulfates, carbonates, phosphates are mostly insoluble in liquid ammonia. Okay. First, we are discussing about the physical properties of the ammonia. So, in these physical properties, so the liquid ammonia, it is acting as the non-aqueous solvent. So why it is taken as a non-aqueous solvent? Because it is a protic solvent and many substances are dissolved in this liquid ammonia and it is having the melting point, boiling point values and the conductivity values and dielectric values. But due to the low dielectric value, due to the low dielectric constant values, it is acting as a poor solvent. That's why all the inorganic substances are not dissolving this. as well as it is having a better character. That is, when the covalent character is increases, then those are easily dissolved in the solubility is increases. Covalent character of the substance is increases, then the solubility nature also increases in the ammonia. Then the second property is that auto-ionization of liquid ammonia. Already we are discussing that. If we can take 2 moles of ammonia is dissolved in auto-ionization, then it is converted to ammonium ion and NH2 minus. The next is about on the basis of auto-ionization of liquid ammonia, as shown above, it is said that any substance which gives ammonium ion in liquid ammonia is a amino acid. Suppose we can take ammonium chloride is called as amino acid because when ammonium chloride is ionized to NH4Cl, this is called as amino acid because this is ionized to NH4 plus and Cl minus. So it reduces the proton. So that's why it is acting as a solvent. Just like this sodium amide. Okay, it is called as base. Sodium amide is converted to Na plus and NH2 minus. It is having the both sides. The interaction of an amino acid and an amino base gives a salt is called amino salt. Okay, so this ammonia is having it produces the amino acids and amino bases, and both are mixed, then it produces a salt. Then what are the chemical reactions of liquid ammonia? So look at this. The reactions of amino acids. As already started, the amino acids are the substances which in liquid ammonia gives NH4 plus ions. Already it is studied in previously that the ammonia itself dissolving, it is involved in the auto-ionization, it produces the NH4 plus ions. Okay. Then the liquid ammonia solution of ammonium salt can react with the active metal to give hydrogen gas. So here NH4 plus, it is reacted with the sodium, then it is converted to, then it produces the hydrogen gas. When ammonium bromide, it is reacted with a base, it produces the solvent of ammonia. Then number 2 is the reactions of amino base. What are the reactions of amino base? Look at this here, the silver nitrate, it is reacted with a base, it produces amine component. Then in this second reaction, the lead iodide is reacted with potassium amide. In the presence of the liquid ammonia, it is produced imine. Okay, so that's why this liquid ammonia in the presence of the base and the metal, it produces amine, imines and nitrite products. The next is about neutralization reaction. This is called as acid-base reaction. In these reactions, amino acids and amino bases react together and give amino salts. Okay, this is called as neutralization. Neutralization is nothing but one acid is reacted with base and produces salt and water. That is called as neutralization reaction. So in this, ammonia also involved in the neutralization. in the presence of the acid and base. We can take the amino acid and amino base, then they produce salt. Okay, like this. Ammonium chloride is called as amino acid. Sodamide, it is called as amino base. In the presence of liquid ammonia, it produces the sodium chloride. It is called as amino salt and it produces the solvent like NH3. Okay, these are some of the examples of the reaction. Then it is involved in the precipitation reactions also. The potassium iodide, it is reacted with ammonium chloride. In the presence of the liquid ammonia, it produces a precipitate by precipitate of potassium chloride and ammonium iodide. So these are the another examples, that is calcium nitrate as well as zinc nitrate. They also produce the various types of precipitations. The next is about solvolysis reaction. So what is solvolysis reaction? Solvolysis resembles hydrolysis. Solvolysis is nothing but a hydrolysis reaction. The interaction of the cation or anion or both with water is called hydrolysis. Okay, the interaction of the cation or anion or both with interaction of the water is called as hydrolysis. Here we can take the NH4 plus. This is the cation. It is reacted with the water or involved in the hydrolysis. It is converted to ammonium hydroxide. If we can take the acetate ion is called as anion. It is involved in the hydrolysis. It produces the acetic acid. Okay. So like this, the sum of the reactions are there. Next is solvation reaction. When one or more molecules, when one or more solvent molecules are attached to solute particle, which may be a cation or may be anion or a neutral molecule. By any of the chemical linkage, the reaction is known as solvation reaction. Once I repeat, when one or more solvent molecules are attached to the solute species by the chemical linkage is called as solvation reaction. In solvation reaction, liquid ammonia is bonded to the solute molecule, that is BF3, and it is linked to the BF3 is linked to the ammonia and it produces a complex-like compound. So that type of reactions are called as solvation reaction. The next is about the solutions of metal in liquid ammonia. Solutions of metals in liquid ammonia. The liquid ammonia is a good solvent for metals. Alkaline earth metals are readily dissolved in liquid ammonia and give metal ammonia solution. These are blue in color in dilute and bronze color in concentration solution. Okay, so solutions of metal in liquid ammonia. The liquid ammonia, it is acting as a good solvent for the metals, alkali metals, alkaline earth metals. Okay. So these solutions are blue color in the dilute solution and branch color in the concentrated solution. The blue color solutions are excellent, acting as the excellent electrolytes. The branch color solutions are with a high thermal coefficient of electrical conductance. Okay. Then by simply evaporating the alkali metal ammonia solution, alkali metal can be removed. The blue metal ammonia dilute solutions are paramagnetic in character. So it is explained by the mechanism. The metal it is converted to M plus and electron. So this M plus cation is reacted with the solvent. Then it is converted to ammoniated cation. Then the electron is reacted with another NH3. Then it is converted to ammoniated electron. Okay, these are in the equilibrium, then produce this type of structure. Next is about complex formation. So, this ammonia is reacted with others and produce the complexes. Many complex formation reactions are reported, many reactions that did not occur in water, occurred in liquid ammonia only. For example, many insoluble metals, imides and nitrites dissolve in the solution of potassium amide in liquid ammonia to form a soluble amido complex. Let us see the zinc amine. Diamino zinc it is reacted with potassium amide. In the presence of the liquid ammonia, it produces a amido complex. Aluminium also reacted with ammonia. In liquid ammonia, it produces the soluble and insoluble complex. Okay. Then it is involved in the redox reaction also. For example, NH3 under oxidation, it is converted to nitric oxide. Copper oxide, in the presence of the NH3, it is converted to copper. So like here, the various reactions are produced. The next is about liquid hydrogen. HF, liquid hydrogen fluoride as a solvent. This HF also acting as the solvent because it is having the same characteristics of autoionization, acid-base reactions in hydrogen fluoride. Then it is also involved in the precipitation reaction and it is also involved in the coordination character. So due to that reason, this liquid hydrogen fluoride is also called as the solvent because its dielectric constant values, dipole moment and solubility character. So in this non-aqueous solvent, we are discussing about types of solvents. What is the why ammonia is acting as the non-aqueous solvent and why the hydrogen fluoride is acting as the non-aqueous solvent. So 3 questions are from this topic. Okay, thank you.